This launch is the boy-girl paradox, which is actually a very famous probability question. If you Google this, you could read some articles online about the history behind this paradox. There are kind of two different answers that people give. So the idea is that you have one child, you're planning to have a second child, and your first child is a girl. So the question is, what is the probability that both children are girls? So the direction that some mathematicians take is they say, all right, well, every time you have a child, there's this 50-50 chance of having a boy or a girl. As a side note, this problem is from like the 50s, so this was back when kind of people only thought in terms of this gender binary of boy or girl. So now there's more complex understanding of gender as like a spectrum. For the sake of this problem, we're going to stick with the idea of 50% chance of girl, 50% chance of boy. So in that case, we would say the probability of having a girl would be 1 out of the 2 possible options in the sample space, or a probability of 50%. So the other way of thinking about this is thinking, okay, I'm looking for the probability of having 2 girls, or the probability of having a girl and another girl. We know in probability from class on Monday that whenever we see the word and, we're going to multiply. So the probability of 2 things happening, this and this, girl and girl, would be 1/2 times 1/2, which is 1/4, which would be a 25% probability. So actually, either one of these answers that you came up with is correct. It just kind of depends how you argue it, which way you look at it. Some people would say you have a 25% chance of having both children be girls. Some would say you have a 50% chance. Okay, so moving on, another way to organize this problem is to create a Punnett square, or a visual representation of all the possible outcomes in the sample space. So one side of the Punnett square is going to represent your first child. One side is going to represent your second child. For child 1, we have 2 possible outcomes, boy or girl. Same thing for child 2, boy or girl. And this is just a way to visually help us organize the different combinations of outcomes. So for example, one possibility is you have 2 boys, you have 2 sons. One possibility is your first child is a girl, your second child is a boy. We could flip that and say maybe your first child is a boy and your second child is a girl. And then finally we could say, okay, the probability of having 2 daughters, 2 girls. So this is a visual way to see this 25% probability, because if I were to say the probability of girl and girl, I can visually see that that's one possible outcome out of the 4 possible outcomes in my sample space. So I can visually get that same number, 1 out of 4, or 25%. And whether you use the multiplication here, or you use like a visual representation to calculate, you should always get the same answer. And you might want to do both just to double check. All right, so moving on to the example 1. Says, assume you are planning to have 2 children at some point in your life. Your first child will either be born as a male or a female. Your second child will be born as either a male or a female. What are the possible combinations of male-female children you could have? Find the sample space for this random experiment. Make sure to include both a visual map as well as a final answer that includes the appropriate symbols such as S and brackets. So this word sample space that I used a few times in the launch, the definition of this is all possible outcomes. So we're going to visually represent that using a visual map. A visual map is the same thing as the Punnett square, a way to like visually represent the different combinations of outcomes. So it's actually going to be the same Punnett square as the launch. We have boy, girl, being careful to label child 1 and child 2. And then representing the different combinations. Now I'm also going to represent this as a list with an S in brackets. So the way we'd represent the sample space here is we'd say the sample space equals, and then I'm going to make a list of all these different combinations from the Punnett square. So boy, I may just say like BB, GB, BG, and finally GG. So if I have 4 squares in my Punnett square, I'm also going to have 4 options, a list of 4 options in my sample space. So we're going to represent sample spaces both with Punnett squares and lists. So you should get used to seeing both. For this second example, same idea. I'm going to be creating a visual map and a list, but now my experiment is that I'm rolling 2 4-sided dice. So as a side note here, whenever 2 things are happening at once, so we're talking about 2 children or we're talking about 2 dice, in probability we call this a complex event, just meaning more than one thing is happening. As you can imagine, most things in the real world are complex events. There's more than one thing happening. So this time, one side is going to represent dice 1, one side is going to represent dice 2, and the possible outcomes for dice 1, 1, 2, 3, 4, because it's a 4-sided dice. Options for dice 2 are also 1, 2, 3, 4. I'm going to organize this, and this is going to allow me to visually combine all the different things that could happen. I could roll a 1 and a 1. I could roll a 1 and a 2, a 1 and a 3, a 1 and a 4, and so on, to create my whole map. All right, and then B asks, what is the probability of rolling snake eyes, which is 2 1s? So now I can see, well, let's actually do it both ways. Let's first use the multiplication rule. So the probability of rolling 2 1s using the multiplication rule would be the probability of rolling 1 1 1 multiplied by the probability of rolling a second 1. So the probability of the first 1 would be 1 in 4, because it's a 4-sided dice. The probability of rolling the second 1 would be 1 in 4, giving me a total probability of 1 in 16. And the probability of rolling 2 1s, I can also calculate that same answer by using my visual map here. So I can see visually here is the combination I'm looking for, this snake eyes, 1 1. And I can see that that is one possible combination out of the 16 possible. All right, so examples 3 and 4 actually use the same situations, so you don't have to redraw the Punnett squares. You can use these squares that you've already drawn to solve questions 3 and 4. and then move directly onto the exit ticket on the last 2 pages. This exit ticket is not graded, it's just a chance for you to check your own understanding. The answer key for this whole packet is going to be linked in the link below, so you can use that to check your work for the rest of the packet. All right, work hard.